Okay, so welcome everyone. So today we're gonna continue with what we were doing last time, which is Spark streaming and Apache Kafka, and using both of them, and then we'll get to today's objective, which is online experimentation. So before that, does anybody have any questions regarding streaming in general? If not, let's actually just revisit the objectives from last time and then pick up where we stopped. Last time we had a very simple instantiation of Kafka system or a streaming system where we had a producer and a consumer, and we had very simple examples of a producer submitting essentially strings to the Kafka single node Kafka cluster, and then a consumer just reading those strings from the cluster. Okay, so let's go back to our objectives. So what we want to do today, for at least first part of today, is to learn the basics of streaming with Apache Kafka, and then be able to differentiate between a batch PySpark workflow and a PySpark streaming workflow on Databricks. Okay, so those are the two things we'll do. So and then we'll get to the online experimentation, and there the objectives are going to be to know the various considerations that go behind doing A/B testing of models before rolling out the models fully. So typically you would roll out a machine learning model on a small percentage of your users, let's say 5% or 10%, and then see how it works, and then you will roll out fully, for example. Okay, and so we'll also revisit some statistical hypothesis tests and particular how sample sizes are determined for these hypothesis tests. And then we'll come back to our model deployment objectives. So we'll create a very simple experiment using a package called Planout. It's a 5-year-old package from researchers at Facebook. So we'll use that open source package to set up a very simple experimental setup. Okay, so it's gonna reuse our material from our first session. So we're gonna use both the surprise-lib based model as well as the PyTorch based model, and see how you can log experimental results for each, I guess in this case, A and B variations of the test, and then use a hypothesis test to conduct, to make a decision. Okay. So those are the objectives. So 2 objectives from last time and 3 objectives from today. So let's get started. So I'm going to briefly revisit, what we're discussing about Kafka. Kafka is just an example of in particular, this is based on Java and Scala, but it's an open source streaming solution that allows one to stream messages. As I said, as we were discussing last time, messages are basically objects like data or some JSON objects. And you should imagine them to be getting produced by some locations or some components in your whole system. They're getting produced and they're being sent to this Kafka cluster, where they're essentially getting logged. Okay, so they think of it as an intermediate storage from which some downstream consumers can read these messages. So instead of the downstream consumers, for example, a machine learning model which wants to perform inference, instead of that model reading a test feature vector from an S3 location or a disk, they can read from the Kafka cluster. Okay, and then that consumer of this, of this input, if you're doing inference, that can read that input from Kafka cluster, do some processing, in this case do an inference, which is to make the prediction, get a prediction, for example class label or recommended items, for example, and then the output of the inference step can again be sent back to the Kafka cluster. In this case, the ML model or the ML model component is acting as a producer again. Okay, so that's how you need to think about it. So you essentially reading from a different location. And streaming just means as soon as the new message comes, you can trigger your model to immediately do an inference and produce the prediction, for example. Okay, so Kafka is just one example of several streaming solutions. Not just for, some of them are centric to machine learning, some of them are actually quite generic. And so this is a little bit older, it's a mature software. It's from 2011. And it has various features. You can see, from its webpage, they say it's high throughput in terms of message, transiting messages from various producers to various consumers. It's scalable because it's actually operating in a cluster. So we are really thinking of not a single, machine solutions here for streaming workflows, for example. And so it's the same even for batch workflows. As Spark, we had a cluster. Kubernetes, there was a cluster. EKS or ECS, there was a cluster, and so on. So they also store messages, and these messages have some lifetime and so on that you can configure. So there are many different features that they list on the webpage. But if you come back to the architecture, let's focus on this diagram. It's essentially a bunch of computers. Okay, so these computers are maintaining essentially a copy of messages being sent to them by producers. So there could be different machines, or for example, these producers could be multiple Android phones. Maybe your app is installed on a million phones. So a million producers are producing client events to this cluster, for example. Okay, are producing messages which are sent to this cluster. And then from this cluster, several consumers, maybe you have multiple copies of your machine learning model, for example, in a container. So they can all read from the same Kafka cluster, make an inference, and send back recommendations. Okay, and maybe that sent back recommendations can go directly to producers, or it can go to the cluster from which, again, some other consumer, maybe the Android app or iPhone, iOS app, can read from the cluster, for example. This is just an example. But all I'm saying is producers produce content or data or messages, and consumers consume those messages. And sometimes consumers can transform those messages, and they can become producers again, and they can send messages back to the cluster. Okay. So this is really and we really have to be scalable. So there's several machines underlying here. But in terms of organization of the messages, they are organized into what are called partitions, and those partitions are organized into what is called a topic. Okay, so when a producer and consumer, so when producer produces a message relevant to a consumer, both producer and consumer have to subscribe to the same topic. Okay, so just think of a topic as a folder, and these partitions, which are just collections of messages, they're replicated across the individual machines of the cluster for fault tolerance, essentially. And these individual machines, are called brokers. Okay, so that's roughly the setup here. And let's actually redo the steps that we did last time with the virtual machine. So again, we'll set up Kafka, and then set up a simple producer consumer instance, and then move on to using Spark streaming to do the job of production as well as consumption. Okay, so let's deploy a single machine. So we're going to create a single node cluster, essentially, Kafka cluster. So let's do that. So let's pick Ubuntu. So this is a different interface than Amazon EC2, but I think it serves our purpose. So let's pick those choices, and we don't need any of this stuff. I mean, we can keep it all default, and let's click deploy. Okay, so this is the instance that is just getting installed. So let's, okay, it's not yet started. So in the meantime, let's start our start a terminal. Okay. Okay, so we have some IP. We're gonna log into that machine. I don't know, is it still setting up? Okay, let's copy the password. Okay, so we just logged in. So, I mean, so we're going to do the rest of the exercise using the root account. Ideally, you should create another account, and that's just 2 steps, add user, something like Teja or something. So, but we'll just use the root account for now. Okay. Um, okay, for simplicity, okay, I think we'll need SSH access. So, um, so what I'm going to do is copy my public keys here. Okay, I copied the public keys. Now, okay, I think we can, okay, so let's do, the IP address. Okay, you saw that this time I did not have to write the, um, give a password. Okay, so that's good. Now I'm gonna enable, sorry, there's no need for a sudo because we're already in the root accounts. We'll do your w hello 22. So UFW is a firewall, and it's available on Ubuntu systems or Debian-based systems. We'll also enable the firewall. Disrupt connections. Okay, so that's good. So we have SSH-based access to the system. We also have password-based access. I did not disable it yet, but I think we'll move forward from that. It's good to disable it, but for this demo, I'm just going to keep it on. So next, we're going to install Kafka. So let's do apt get update. Oh, sorry, apt update. Okay, now there's some packages that can be upgraded, but that's okay. So let's install a version of Java runtime. So this is actually OpenJDK, but you can also install um, Oracle's Java version. Okay, next let's get the Kafka zip file, and then let's unzip it. Let's go into that folder. So I think, so at this point, last time we also used screen. So screen is just for terminals within a terminal because I didn't want to use too many terminals tabs here. So let me just give a name called Kafka for the session. So we are inside a screen session. You can navigate across screen sessions using Control A, Control N, Control A N, Control A P. So Control A C will create a new terminal. So a new virtual terminal. So these are the two virtual terminals I have. Okay. There's something we covered in the first session. So okay, so we have a screen session. Next, what we're going to do is start a auxiliary program called Zookeeper. It's in the, so if you look at this directory, it has bin and it has a bunch of programs inside the bin or binary directory. So we'll start Zookeeper first. It's just a temporary synchronization software, synchronization program for Kafka, but it will be removed soon. So we started that. Next, we can do a Control A N or Control A Control C to create a new terminal, and start Kafka itself. Okay, so now Kafka itself is running. So what we need to do is to next create a topic. And then create a, so Kafka itself is running. So right now it's running on localhost. So it has a particular port to which, through which you can communicate with it. We're gonna make it exposed to the world in a few minutes, so that there's using the public IP address that we have. But let's first create a topic. Control A C. And so all you're saying is Kafka topics hyphen create a topic with a name. We're just calling it quick start events, as you know, because we're relying on the quick start tutorial here. And minus minus bootstrap server is just saying which, you know, which is the server which is currently a local host of this machine, and the port is 1992. So it's a default choice. Okay. Okay, so we created a topic. So now what we've done is started Zookeeper and therefore started Kafka, and subsequently started the Kafka server. So that essentially is running as a single node cluster. So ideally you should have Kafka running on multiple brokers essentially, but we, for demo purposes, we are just doing it in a single machine. And how do you change those things? Recall that we were doing um, config. So for example, ls config has all sorts of configs. So it has the config for the server where you can change a lot of things, a config for Zookeeper as well. So so now we have created a topic. Okay, so now the Kafka server is running with the topic instantiated. Now all we need to do is send messages from producer to this topic, and if another consumer is connected to this topic, then they can read those messages. So let's do that. And according to the quick start, there's a simple producer that can attach to, so there's a producer script that can attach to this particular topic and copies quick start events at this server. Okay, so there's a simple producer that we're going to attach. This producer is just going to let you type something on the terminal, and whatever you type, and you know, in a line, that gets sent as a message. Okay, so let's start this producer here. Okay, so you'll not see anything except for a bracket here. So let's say hi. And then let's create a consumer. So, okay, so I created another terminal inside the screen session. And yeah. So this command is basically saying, okay, let's create a consumer. So you can look at the shell script, but it's saying this consumer should start connecting, you know, it should connect to the topic quick start events and start getting the messages from the beginning. Okay, so instead of from beginning, you could have said, you know, latest, then it will only, although it connects to the producer and there could be previous messages sent by producer to this topic, some other producers to this topic, you may not read it. Okay, but with from beginning, it's going to read all the messages the first time it connects to this topic. Okay, even if the messages have come before this consumer, you know, started, right? So if I hit this, you should be able to see the hi first message. Okay, so we got the message. This message was read from the Kafka cluster. Okay, so that's good. So now what we're going to do is do the same with a Jupyter notebook. Okay, and for that, what we're going to do is yeah, so for that, let me use the previous SSH login that I had. So let's change this. So let's install. So this time, the way I'm going to set up Jupyter Notebook is not through Conda. So this is just give you a sense of that you don't really need to rely on Conda for a Jupyter server, right? In session one, we did that, but here let's install Jupyter directly. Okay, so now we're installing Python 3. So what we're going to do is instead of Conda environment, the way, for example, in my local machine, this is running under a Jupyter, under a Jupyter environment, right? So this Jupyter, which is running on my local, in this case, a Mac machine, that's running under the Conda environment datasci-dev, and that's what we've been using over the past few weeks, right? So past few sessions. But here I'm going to create a Jupyter server on this public machine, which is running via a virtual environment. Okay, so a different virtual environment. In particular, we're going to use the virtual env package in the Python ecosystem. So let me install pip. So pip3 is installing pip because it's needed for subsequent installations, automated installations. So after installing that, let's um, yeah, so because we want to make a virtual environment, so we are in the root directory. So let's make a virtual environment. Typically is contained in a directory. So in the case of Conda, the virtual environment is actually the files related to the virtual environment. If you install Miniconda, it's in the Miniconda directory /n/ your virtual environment name. So instead of that, so we're going to create a Jupyter N. So let's call it Jupyter environment. And then let's go into Jupyter environment. And okay, first we also need to install virtual env package. So let's do that. Okay, so now in this directory, I mean, you can put the directory anywhere, but in Jupyter N directory, we're gonna we're gonna create the virtual environment. So virtual env. I mean, you can give the same name, but Jupyter dev, sorry, Jupyter N, but it doesn't have to be the same name. So we can give a different name, but let's use the same name. Okay, so it says created a virtual environment, right? So now what you do is we can, so what happened with that, right? So there's a local directory, Jupyter N, and inside that you will see all the Python binaries, for example. Okay, so you can see pip and Python and so on, okay? So let's go back. And here in this directory, let's do source activate source. You will see what this command is doing is to get into this virtual environment, very similar to Conda activate the virtual environment name. Here it's slightly different. Okay, now you can see we are in this particular virtual environment. Okay. Next, what we can do is in this environment we can install Jupyter. And we'll also install another helper package, which will let us talk to Kafka. See, the next few minutes, what we're trying to do is to use the Kafka's producer and consumer APIs and use them to subscribe to a topic and push messages to that topic and consume messages from the topic. And we're going to do that, and these API access is through, so Kafka itself has these APIs, and we have Python bindings for those APIs. And so for that is through this package called Kafka-Python. Yeah. Okay, so we install Jupyter and Kafka-Python. Let's create a config and then create a password. This is just to avoid the issue of the token getting auto-generated and so on. So let's see. Okay, so I created a password. Next, what we're going to do is yeah, next, let me just run Jupyter directly instead of a screen session. I'm going to terminate it probably after some time anyway. So Jupyter Notebook port, and I have an extra command line option here, -- allow root. That's only because I'm working with the root environment here. But ideally, we should have switched. If we started with the Ubuntu system, there's a add user, for example, Teja is the initial command, and you can switch to that user and do everything in that user so that you don't have to have the extra command line argument. Okay, so we started this. Now, what we're going to do is go back to our uh, local machine, create another terminal, and here we're going to do an SSH tunneling. Okay, so this is only to get to the access to Jupyter, which is running on that remote machine. So let's say it's 9999, it's fine. So 144, 202, 7, 4. Okay, so this enables the tunneling. And then I'm going to open a new tab and do localhost 9999. Yeah, so now okay, so now this is actually running on the remote machine that we just started and logged in. So you can see how quickly you can rent a machine and get started. Let's now create a yeah. So now what we're going to do is create a simple notebook and try out the accessing the local Kafka installation. And send some messages to it. Okay, so I have look at the notes. I believe I have yeah. So what we have gotten to is up to this point where we have tunneled and we have a working installation of Jupyter Notebook. And what we're going to do is now push events and read events from the local Kafka installation. Okay, so in particular from this topic, quick start -events. And in particular, we're going to use the producer API. So let's actually get the information. Let's actually leave it as HTML. And okay, so this command is just saying connect to the local, cluster. It's just localhost, and there's an extra argument to the Kafka producer class, which is it's saying how do you how do you deserialize? Sorry, how do you serialize? Which is basically JSON dumps. So you're basically encoding it as a JSON object. Okay, so it makes sense if you want to send a dictionary even instead of a string and so on. So that, and then so here I'm sending a list, but I could have sent a dictionary as well. So let's see, let's send this dictionary. Okay. And since we sent that dictionary to the producer as a producer to the Kafka instance, then we should be able to see the outcome. So you can see this was the consumer. It read hi, it read a colon one as well. So recall this producer only produced hi. So you can say if it produced hi two, then this consumer has read from the first producer, from the second producer, from our Jupyter notebook, and now it's read back from the first producer hi two. Okay. Now if I control C and terminate this consumer, but restart this consumer, now although the consumer is starting now, it's going to read from the beginning, and these messages are stored in the Kafka cluster, so it's going to get all the messages back. Okay. So, okay, why am I illustrating this? Is because think of it this way. So if you have a component that you need to, fix something or update something and bring it back online, it's not going to miss anything. Of course, messages may get queued if the expectation was that this new, let's say you're doing machine learning model switch. Okay, so you had a previous model, but you want to turn it off and connect to another model. Okay, or change the model in some way. So the piece which is reading from the Kafka cluster, that can be turned off and turned on, and it really would not affect much, unless of course the message queue is growing very quickly, and so you have to catch up. But otherwise, this is one nice feature about using a streaming infrastructure. Okay, so we saw how to produce an event. So now let's also look at how to consume events. So, and for that, we can import a Kafka consumer. So let's do that. Actually, it's there here. So we're importing the Kafka consumer class basically, and we also need JSON loads because we're gonna consume from the topic, from the local cluster, but we're going to deserialize the input. So okay, so we're going to assume that the input is essentially a string. We're going to decode it to UTF-8. This is just a decoding of a string, which could be it's the right thing to do. And then JSON.loads loads it as a essentially a dictionary. Okay, so we are expecting a dictionary here. So take X as an input and produce a dictionary of it out of it. So let's run that. Okay, so from this consumer, if we okay, let's see. Okay, so this consumer we have to so it's running right now. So we should pass in a dictionary, right? So since I have the producer and consumer same notebook, let me go back to my text-based producer and create a dictionary. Okay, so here, or a JSON object, essentially serialized JSON object, so actually a string. So let me just do this and press enter. And then you'll see we have read back the object. Okay, so x dot value is actually a dictionary with key B and output 1. Okay, so this consumer is not reading from beginning. Okay, this consumer is reading, it just started now. So if I now start producing inputs, it's going to be read back here. Of course, since there's I'm applying this lambda function, it expects things which are of this form. Okay, so something like basically a serialized JSON object. Any questions at this point? So what we've done is play with command line producer consumers and Jupyter notebook based producer consumers. If there are no questions, then let's actually move forward to trying to hook this up with our Spark streaming, with the Spark streaming example. Okay, so let me go back to, yeah. So what we're going to do next, as I said, is so few words of caveat, I guess, a few disclaimers is that consuming messages or producing messages from a single machine is not practical. Okay, so if you think of real life Kafka installations, and Kafka has been used quite a bit in several companies in multiple industries, not just for machine learning, although we are interested in machine learning aspects, machine deployment aspects, machine learning deployment. Um, they are generally in a cluster, okay, and that's where it shines, where you have thousands of messages coming in, thousands of messages going out to different producers, different consumers, and so on. Okay, the Kafka API is very scalable in when it works with a bunch of brokers, and we're gonna move with Spark next. So let's do that. Um, Okay, so some background about Spark streaming. So Spark streaming basically relies on the same building blocks of Spark, okay, which is the RDDs and Spark data frames. And RDDs, as you recall, allowed for fast distributed processing of large data sets. So uh, uh, these were distributed uh, uh, instances of data on multiple worker machines in the Spark cluster. Instead of all the processing happening on just a driver, for example, which is what you would do if you would just use pandas or something like that. Because of RDDs and Spark data frames, you can actually do distributed processing of large volumes of data. Okay, and Spark streaming basically relies on the same ideas of Spark, the batch Spark version, to allow for streaming operations. And streaming operations, you can think of just transformation. So the typical transformation that we are interested in is getting an input feature vector and generating a prediction. But you can imagine even an ETL type of transformation where you get an input vector or input, I guess, data, a JSON object, and then you do some manipulation like change from degree Celsius to Kelvin, or maybe change timestamps from UTC to local timestamps or something. So there are many transformations that you can do, and they're all things that you can do with streaming. So in its core, basically Spark Streaming lets us read data as a consumer in fixed small sizes. So if you look at the other consumers that we wrote directly using the Kafka API, they are reading one message at a time. Okay. So in the sense that they get triggered every time a new message is produced by any producer. Whereas to make Spark streaming work, reuse all the underlying blocks as the batch version, there has to be some batching going on, okay, at some point, because streaming has to work, reuse all the pretty much the same software as batching. So what it does is it works with data in fixed small sizes, okay, and then converts those. So it's like batch, a batch for the next 5 seconds or next, 1 second, and send that batch of data, convert them into RDDs, and then do processing. Okay, so the benefit of this is that Spark Streaming basically uses the same code base for batch. But the downside is that there's a little bit of latency, right? Once you create a small batch, then there's going to be some latency involved. And the latency can be reduced by reducing the batch size. But if you're reducing the batch size, you're not really exploiting the distributed nature of your Spark cluster. Okay. Spark Streaming itself has interface with Kafka, which is what we're going to do now, but it also has several interfaces with many other streaming systems. Okay, and one popular streaming system, which is a managed solution, is Amazon Kinesis. So I think in the exercises, there's some comments about this. So what is the business objective for bringing in machine ML deployments or doing ML inference in a streaming setting? Okay, so the objective is the business objective here is that a streaming PySpark based ML deployment pipeline is going to ensure that predictions don't go stale. Okay, what do I mean by that? You can actually, so for example, think of a batch pipeline, batch workflow, where your model is generating predictions every night, okay, or every week, okay, which means that, so let's say it's producing every week, then the predictions were made on Sunday night. The same predictions have to be used again and again for downstream decision making, whether it's Monday or Wednesday or Friday and so on. So on Friday, maybe these predictions are old, okay, because by Friday, maybe the user feature has evolved to a slightly different feature vector, okay. But if you could apply your model to the slightly, the newer feature vector and get new predictions, then that would be more useful. And that's exactly, what Spark streaming enables. And if folks are already working on Spark batch pipelines, then streaming is not a big delta compared to some other, trying to do something different from scratch to get to a real-time or more fresh predictions. Okay. So what's the general, what's our setup? We're gonna set up a Spark PySpark function that reads input from an input stream. Okay, and the input stream is going to be from the Kafka cluster, applies our model. Okay, or any transformation actually, but applies a model and sends its output to an output stream. Okay, so that means there have to be two topics actually. Ideally, we prefer, for example, we in the current simple toy example, we did quick start events as a topic. Similarly, you can, instead of quick start events, you could have a features topic and a predictions topic. Okay, or inputs topic and predicted outputs topic. Okay, so that the PySpark function can read from the inputs topic and dump predictions to the prediction outputs topic. Okay. Much of the complexity going from a batch to streaming is actually hidden behind the scenes, so that if your business requirement is to get real-time fresh predictions, you can actually easily set up a streaming job in for example a vendor like Databricks or your own self-hosted Spark cluster relatively easily, which was virtually impossible before. But thanks to all these technologies, you can actually really be able to support a real-time ML prediction or inference service. Okay. So we'll see. So we'll set up a streaming pipeline which gets information from a specific Kafka topic. I mean, we'll actually just use quick start events. Uses a prediction model that we already have. I think we're going to use surprise later on, and write the output to a new topic. Okay, and that's going to be the predicted recommendations, for example. And as I think I pointed this out before, is that the key benefit is that if we stop our PySpark, cluster with needed maintenance, or it had to go down for some other reason and we had to recreate our cluster, then our PySpark consumer and producer can still, can still plug back into the system, and the system will still work as is, right? Nothing else has to be changed. It's just that there'll be a backlog of messages that need to be processed. Okay, so for that, let's now actually expose our Kafka cluster to by attaching, by ensuring that it is accessible from an external IP, so from external machines. So with that, to do that, we need to edit the, we need to restart the Kafka cluster. So let's do that. So this is Jupyter, and this is where we're running. Okay, so actually, if you're going to restart the machine, but with an external access, then let's see how it works. So this is where we were doing. Okay, I killed the zookeeper. Okay, this is. Okay, I should have killed the. Okay, so I stopped the Kafka service. Now what I'm going to do is edit the server properties. Yeah, so here, I think this is line 36. Oh. Yeah, line 36. We can change advertise business to equal to plain text colon and your host name. So our host name is our IP address. So let's add that. Okay, so we added our IP address. Okay. Now we'll also need to recall we had the firewall. So if w status verbose will tell us, what port is, like external machines can only access to port 22, but we need to give access to port 90, 92 as well. So okay, so we just enable that port. Um, so now what we're going to do is, so that's good. So let's restart Kafka server, but let me see if Zookeeper is running. Okay, um, okay, let's run Zookeeper again, and then run Kafka server again. Okay, and next a lot of info logs, but okay, let's terminate this. So this is the producer and consumer, which we did not terminate. So yeah, so we don't need these two anyway at the moment. We can start them as needed. So now let's actually go back to um, our local machine. So this is now not the Jupyter from the remote machine, but our local machine. So let's create a new notebook, and actually let's copy all this, except we'll change it from localhost to the external IP that we have. Okay. Home page. Where does this notebook go? Okay, so here. Let's actually send it closer to. So this is on Mac or a local machine on remote. Okay. Let's copy this, and we'll also change the local host to this. Oh, okay. On the local machine, I did not install um, Kafka Python. So let me just quickly install that offline. Um, okay, so let me restart this kernel. Okay. Um, okay, this is saying no broker available. It's the Kafka instance running. Okay, how about this? This should also, oh, because this consumer is still running. Let's terminate the consumer. Let's see. Okay. Okay, it's still running on the local mode, I believe. Um, let's start the consumer. Okay. Um, I'm going to recheck server properties. And this should have been correct. So actually, let's see if, I don't know if Zookeeper also has to be restarted, but let's see if it, okay, somehow we were able to establish connection. Actually, we are more interested in the consumer. Actually, both. Let's do this. Okay, so we were able to send the data, so it didn't error out. So we are able to publicly access this IP on the Kafka cluster. If any of you wants to access it as well, you can access it currently. To just double check that we are actually, we have sent that. So producer's not here. So let's start our consumer here. We just produced again a colon 1. Just double check. We can do 1000, and we should still be able to see that A1000. So we are able to, because this is running on my local machine, we are able to externally access it. Okay, so this is good. I don't think there's a need to consume again. So we have external access. Now, the reason for getting the external access is that we want to, our Spark streaming job is running on a Databricks machine. So the Databricks machine needs to know the IP address for the Kafka machine to be able to interact with it. Typically, in a professional setting, you will have both the Kafka and your Spark cluster in a virtual private cloud, essentially, or a local, or a secure network, so that they can each find each other. But hopefully, external users cannot access these machines directly. But here, just for demonstration sake, we are using an external IP explicitly. So Kafka in this case is running on a Vultr VPS machine, whereas Databricks cluster is currently running on, I think, an AWS machine. Okay, so that is good. So next, let's go to Databricks. Not this one. Yeah. So Databricks, I just started sorry, I should have called it rec, but I started a cluster just at the beginning of this session. So let me go to users and click streaming 101. Okay, so this is a notebook that's available on our course page. So I think this is here. You can get the notebook or the HTML version here. So let's go back here. So it says notebook attached. So let's actually attach it to the cluster that we have. So what are we doing now? So we actually, first thing we're doing is import JSON. It's just to deal with JSON objects, pandas, and then we're also importing PySpark SQL types, string type. So this is just specifies the type of the column of a PySpark data frame. Okay. So here is a very simple function called recommend. it's a dummy function. Currently, what it's going to do is, so a PySpark data frame is essentially a bunch of rows, like because it's essentially a SQL table. Uh, uh, you know, you can think of it that way, although its underlying thing is an RTD. So we can access a row, so you can do a row-wise function application, right? So just like apply for pandas, apply is a function that you can, with which you can apply a function on every element of a column or multiple columns in a pandas data frame. Similarly, here this function we're gonna think of it as, if think of it as applying to every row of a Spark data frame. Okay, so if row is an input, okay, so we're gonna do JSON.load. So we're going to convert it into a dictionary. And then we're going to use whatever we converted from that row. In particular, we're going to use the UID column. So UID is the user ID. So we're just going to reply back saying, oh, here's the UID that I obtained. Predictions, there's no predictions. Okay. And I'm going to return by first creating from a JSON. So I'm going to return by first converting the result to a JSON object. So JSON dumps the dictionary to a JSON object, and then I'm creating a string out of it. Okay, and that's what's getting returned. So let's execute this bit just to get everything set up. Okay, so next what we're going to do is, so this is the important part. So what we're doing is calling Spark read stream. So this is Spark streaming. Format is Kafka. It could have been something else like Kinesis or some other streaming format. And then we're going to connect to Kafka Bootstrap servers. So this is just the type of servers that we've been setting up. And the IP address here, we just need to supply our IP address. So let's use that. Okay, and we're going to subscribe to quick start events that was already there, that particular topic. And we're going to just pick the latest latest message in that quick start event. So we're going to only focus on once this. So this is actually a consumer. Okay, it's starting to now consume from, once I execute it, it's going to start consuming from that external service, sorry, from our Kafka cluster. It's going to only focus on the latest messages that are being generated. Okay, so instead of latest, you could have said from beginning and stuff like that. So let's execute that. So now this data frame, although it says it's executed, the data frame is available, it's actually it's a streaming data frame. Okay, so if I look at print schema, you can see we didn't specify any schema, and it's subscribed to a specific topic. You can see this data frame has a key value, which topic, which partition, what's the offset. Offset is think of it as a metadata related to a message, a timestamp, and what is the timestamp? Okay, so there's some bunch of columns in this data frame. What we would be interested in is this value. Okay, so we'll be interested in this value column of this streaming data, or the Spark data frame. That value will contain the latest message, basically. Okay, so before we get to, so what we're going to do in the next cell is cast that value as a string first. Okay, so the value by default is going to look like a binary gibberish. So we're going to cast it as a string. So this cast operation is very similar to any SQL. If you've seen SQL before, so you can cast from string to ints and so on. So we're going to do that. And next two lines are something we have probably not seen before, is the following, right? So we are going to create what is called a user-defined function. Okay, so I don't know if I imported. Okay, so we are going to create a user-defined function which is called recommend_UDF, and it's going to basically a function that we can apply to columns of a data frame. Okay, so we're going to pick up our original, the function that we created called recommend, and that we'll just have to specify what is the output type of that function. So output type is going to be a string, because clearly we are returning a string here, and that's why we imported the string type. So to be able to specify in this user-defined function what is the output type. Okay, the input for this function is going to be a row of a data frame, so that's fine. of a Spark data frame. Output type, we just have to specify the type of the output. And then once we've created this UDF, we can, just like in pandas, where we will do df.apply a function, here we'll do df.select and uh, apply this user defined function on this column called value, right? This is the column which we just cast as a string already, and then we are aliasing this as a value. The name of the column is again value. Okay, so let's run this. But I think UDF. Okay, UDF is already. So UDF is available in Spark, like you can do from PySpark import UDF, but it's already available. So okay, we run this. Okay, so what we're going to do is actually now whatever result was produced. So every time I'm going to send a UID with something, this streaming job is going to run and just reply back by saying, oh, here's the UID you sent me, and predictions currently nothing. Okay, we're going to fill in the predictions soon in the next iteration. And where are we going to send this to? We are going to send it to a topic called recommendation events. We have not yet created it, so let's create that events on our Spark, on our Kafka cluster, and then we're going to do a df.writeStream format Kafka to that IP address. So IP address is this. And sorry. And we have to create this particular topic, and there's an intermediate, where do you want to have like a local temporary scratchpad directory. So that's that, and you keep writing this. So let's execute this. Okay, so this command is will continue to run. So what we can do now is okay. See, is this the right? Streaming query exception. Lost because they're not available in Kafka anymore. Okay, that's fine. Fail on data loss to false. Okay, let's for temporary reasons, let's just do this. Okay, I need to double check. Okay, we're not sending any events, so okay, if there is a error, then I guess I think we'll have to figure out what this error is. I think that makes sense. Okay, I think what I'll do is try to figure out that error. So, okay, so that was writing back the result. So let me just, if I do df here, okay, maybe actually display data frame here. So you can see a different symbol here. It's like stream initializing and running command. So now what I can do is send, so okay, now I can send a job. Okay, so send a message. So what is the message I'm expecting? Just a UID. Yeah, just a UID is what I'm expecting. So Let's do that. Where is our Jupyter notebook? Back. Okay, so what we're going to do is send a data, which is basically UID and 196. If we do this, and then go back to streaming 101, we should be able to see that. Yeah, so you can see, so that message that we sent from a producer, which is my Mac current a producer which just generated this. What we were able to do is that was sent to Kafka, that external IP, right? From Kafka, it was read because it's reading from the stream. And here I'm just displaying the result after it has been transformed. So you can see the data frame got, that particular string was read, UID is equal to 196. That was the value. That value got transformed as string. Where is it? Got transformed as string, and then this UDF was applied, which is the recommend function, and the UDF responded back with the value. Right? It responded back with this string. So instead of prediction here, if I say no preds yet, and if I start with execution, and then restart it, and on Mac, if I let's say send 20, I don't know. So it's going to only take the latest entry. So hopefully this was started before I sent the 20. So okay, I think it did not. I need to re-execute the DF. I mean this part again too, so that it properly picks up the right function. So this function was updated, but I did not update the whole sequence of transformation. So that's why it's not showing no preds yet. But I think that's fairly standard. So what we'll do next. So I think what's missing is I was not able to write predictions back. Oh, okay. I think I was not able to write predictions back. Could be because I did not even create the topic called recommendation events. So let me actually do that. There's this. Okay. So all the okay, before I call producers, yeah, create topic. Let me call it recommendation events. Okay, it's so we created the topic. Maybe this was causing the error there. So let's go back to streaming 101. Let's stop the execution here. Let's run the whole thing again because we just changed the recommend function. Print schema is not needed, but okay. And now we are trying to write back. Okay. Let's see. No, it's the same error. Okay, so just to check that we have updated the function, let me just I'm going to send the same query again, sorry, same message again to the cluster, Spark cluster from which the streaming job is going to pick it up and produce, and we're going to see the output here as no predictions yet. So this error is the previous error. We'll try to fix it during the break if possible. So let's see. Yeah, no predictions yet. So what we're going to do, let's take a quick break. So let's resume at 7:53. In the meantime, I'll try to see if I can fix this. If not, anyway, we'll move forward and try to deploy our machine learning model. Okay. So let's meet back at 7:53. Okay, so let's resume. I could not figure out what the error is. It's mostly something to do with how Spark Streaming is handling the Kafka interface. So let's see this. I don't care. Um, okay, so now let's send a message UID 20 and the streaming. So this query, which is going to write stream, should add a add an output to recommendation events. So how do we check that? Is go to, or actually copy this thing and connect to recommendation events. It's not localhost because on a local machine there is no. Okay, now very similar to this. That's actually the for loop.
Actually, we can't see the screen.
That is a good point. Oh, took some time for us to realize. Okay, now what I did is basically I didn't do much actually. Let's go back here. All I did is so we were trying to debug why we were not able to write from Databricks to why we're not able to produce a message back to the Kafka to be read somewhere else. Okay, so where we left off last time or before the break was at just an extra string. So what I did is to see if we can ignore the fail on data loss. Um, just make the fail on data loss Kafka configuration option set to false. By default, it's true, and so that's what the error said earlier for the query. And so I added it here, and then rest of the cells are the same. And what I've done is instead of display, I just ran query again. It hasn't terminated yet. And then what I did is go back to my local Jupyter notebook, and I had a producer, right? So I can produce a object, produce a message to be sent to the Kafka cluster, which is going to be read by Spark Streaming, and then it's going to hopefully transform this to UID is equal to 20 and preds is equal to no preds yet, okay, which I can read from my Kafka cluster. So let's say I send it again. Then what I was doing was, so this is localhost, this doesn't work. So I was just, I just copied the public URL for my Kafka cluster, ran this, and then I want to read from there. So if the streaming job ran and the writing ran as well, then they should start now displaying additional, start displaying the outputs. So to do that, actually I should run. So I'm running this here. So actually maybe I should run. I need to produce. Um, so this is actually okay. Let me actually stop this. So there's two parts. The first two cells are like related to producer. The next two cells are related to consumer. So let me focus on producing so that it can be consumed by the Spark streaming job. So let's say I ran this instead of 20, let's say 25, just to differentiate. So okay, I produced a single message. Okay, so now this message has to go here, right? This message has to be read by this data frame, which through the subsequent transformations that I've defined will go through this function recommend. Okay, that function recommend is saying, oh, you read this UID. Let me copy that UID to the first element of my response, and the second element of my response, which is the predictions. I'm just gonna respond back by saying no predictions yet. Okay, so that transformation has happened. Now this, so what I'm doing is writing this data frame to my Kafka cluster again, to a different topic called recommendation hyphen events. Okay, so hopefully what we sent with UID 25 has been read and it has been transformed and it has been sent. Now we just need to read it from there, and you see we have actually, so we need to read it from recommendation events. We just set up a consumer from there and we just read it. So we have gotten the two new events. So if I now produce an event, let's say 100, you'll see the same thing. Okay, so produce 100, it went through the Spark machine, powered by the Spark cluster, streaming job, and it got produced. And this is being reflected here. Okay, this is all my local machine. So and the sending producer, I could have sent from the local machine, but I'm sending it from the remote machine. Okay, so all I'm saying is it's so configurable. So you can send messages from anywhere, read messages from anywhere. So I sorry, not that highlighted part. I'm sending messages from this remote machine 144 dot something dot something. It's going to the cluster. From the cluster, Spark streaming job is reading that this string here is processing it, adding extra breads is equal to no breads yet, and then sending it back to the Kafka cluster, from where I'm reading from a local machine, and this is the final thing that I read. Okay, so the whole operation was done. Now what we're going to do, so that's it for the simple execution. So now let's move to our streaming recommendations. Okay, so this is just an example of um, uh, so we're going to set up a streaming streaming setup where the incoming, so somebody's going to submit a UID, user ID. So think of a client and like an app, or an app on Android or iOS, sending their user ID essentially, and sending the user ID to the Kafka cluster. Now, as a so therefore these are producers. Now, once the Kafka cluster gets the user ID, there's a consumer, which is a Spark streaming job, which reads that user ID. For that user ID, it reads the predictions to be made and generates a list of recommended movies, and then send it back to the Kafka cluster to a different topic called recommendation events, from where a client can read the recommended movies. Okay, so here there's information about AWS, but I think last time AWS did not work, so I'm going to delete that. So this, I don't recollect the last time. Okay, let's go to a different. So I'm just going to read it from if it's already there. So if it's not there, then we're going to do it again, but hopefully it's there. So u.data, that's what we wanted. So instead of reading it from S3, ideally you would want to read it from S3 to do anything, but okay, so let's try if this works. Attached to a cluster. Oh yeah, the data set is there. Okay, so now let's install scikit-learn, scikit surprise. So this was one way, quick and easy inside the notebook, but if you want to keep it the same on the cluster, you can always install it from the cluster. That's what we saw, I think, last lecture. Okay, so we're installing a package. Let it run. Okay, so I think it may take some time. Okay, so the installation got finished. So now we're just going to do some standard imports, get the algorithm, get the data set, get a reader object to help facilitate reading the data. Facilitate creating appropriate intermediate data objects, train set, and so on. So okay, let's do this. So next is get predictions. All it's doing is for every prediction, just getting the top end predictions. Okay, so this is just standard function. We have seen it before, so I'm not going to spend time on that. And then we're going to load the data set from the data frame. So we had the data frame. So this data frame here is actually a Spark data frame, by the way. So we converted it into a pandas data frame. Let's actually use the pandas data frame to create a data object. So all this operation is actually running locally on the driver. Okay, so it's not optimized for Spark, but for because my objective right now is just to show the streaming operation, other operations are not optimized. But that's a good exercise to do to get these get this whole setup optimized for a Spark cluster. Okay, so let's train the matrix factorization model. Okay, so by the way, this matrix factorization model may not, running it on a driver when you have a really large number of users and a really large number of movies is not ideal. It's in fact, you'll hit out of memory issues, whether it's on here or on your local machine. So be careful with that. Okay. So let's get the top predictions already. So what it's generating is top predictions for every user in the training data set already. So once this is done, we're just gonna look up, so this is basically think of this is basically a dictionary. So you can look up a user ID and get their predictions, okay, top n predictions, and n is 10 here. So what changed from our previous streaming 101 script is that now the recommend function is gonna start, providing recommendations. And in this case, I'm just, simply producing the list of movie IDs. I'm not even doing the movie IDs to movie names conversion, but you can do that as well. So this is very similar to streaming 101 notebook. So let's run that. Now here, I think we should add there was this issue of a data loss thing. So let's actually go back to that notebook. So if you leave the notebook, it's not gonna um, clear up. So it's fine that way. So we're here. So we're gonna read uh, the query from quick streams events topic. I mean, instead of quick start, instead of quick starts, I could have said user ID events or something like that. That, a separate topic where clients would send user IDs and the Spark streaming job would send recommendations to recommendation events topic. Okay. So, but let's keep it simple. So we'll also change the IP address. To the right Kafka instance. Let's do that. Okay. Now, so we have done that. So what we've done is read from the, so we've created a consumer. The consumer is also, going to transform. So these three steps are essentially transforming the value column with the value object, which happens to be in binary format. So we're just casting it as string and then using the string to read the user ID, D bracket user ID basically. Convert it into a dictionary and then read the user ID. And then given the user ID, we are looking into top n, this is a dictionary. So we're looking into the recommendations for this user ID and just dumping it out. Okay. So let's run, let's report back the predictions. Okay. So this thing will continue to run as long as you keep the cluster on. So you can actually see that if you go to clusters, so if you click on it and go to notebooks, you will see that streaming X is going to continue to run. So it's a streaming job, it will continue to run. So what now we need to do is to test the same way we were doing before. So let's create a new user ID that we want to recommendations for. Let's say it's 196 for simplicity. We ran it. Okay, so now we have submitted this user ID and this user ID to the cluster. Streaming job is being run, so it must have produced recommendations, must have dumped it to the recommendations events topic. And so since we have already a consumer, okay, this has not dumped. So let's double check that. Ideally, we should have seen the predictions here, but let's see. So workspace. Okay. So this is did not go there because the IP address isn't correct. So let's change that. Okay, now the loop is complete. So let's now go back to remote, again generate this user ID, and we should see a result immediately. Okay, so Okay, so the previous two results have been written down. So these are the predicted movies. Okay, I'm not transforming them back to movie names, but you could do that by reading the movie metadata file and so on. Okay, so 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 this is how this is what a client could do. So send a user ID and wait for this user ID. These are the predictions and map back to movie, like posters or whatever it is. Okay, so just to check one more, let's say. Wow, so it was near instantaneous. We got the movie IDs back. So any questions about this part? So we just did streaming recommendations. Although we did very bare bones, and there are a lot of parts which can be improved, especially in production setting. But this is a bare bones streaming job for, say, movie recommendations. Okay, if there are no questions, then let me go back to our notes and conclude the streaming section. So yeah, so basically although I quickly demonstrated a simple non-ML streaming job, and then we attached a streaming job in the Spark streaming setting, as well as we tried out how Kafka itself works using Jupyter Notebook, as well as using the quick start producer consumer scripts. We've only scratched the surface because essentially we were playing with a single broker or a single machine Kafka deployment. Right now it's not even secure because it's publicly accessible. Anybody can write to the topics that I showed you, like you guys can try as well. So there are a lot of things that we did not touch upon. Okay, and but it's not like you will probably support a Kafka cluster yourself, but you may be expected, or in data science workflows, you may be expected to create a streaming job which reads from a streaming platform like Kafka or Kinesis, and generate predictions which also go back to a streaming platform. Okay, so that part, which is actually pretty much we saw it in Databricks environment, but it can be done elsewhere as well. For example, in a Jupyter, in a regular Jupyter instance as well. Okay. So streaming pipelines are increasingly popular, especially provide real-time capability with a lot of benefits. Like you can turn on and off some producers, consumers. It doesn't affect the rest of the system. We saw that earlier. And kind of a central part of many analytics focused organizations and companies. Being acquainted with what these technologies bring to the table, and is useful to create scalable ML model workflows for both training and deployment. Training was mostly we saw with, for example, Spark and others, and deployment where we saw several technologies, right? So it's a good skill to have. So let me mention a few exercises before I jump to online experimentation. So you can actually, instead of Kafka, which is where we spend most, 100% of our time here, you can also try out how to work with Kinesis, and you can certainly go through its quick start. Kinesis is going to have very similar like overall pattern of producers producing messages and consumers consuming messages. It's a managed streaming platform, unlike Kafka. Actually, there are managed versions of Kafka as well, um, um, being provided by many of these cloud vendors. And they have actually, if you go to Kinesis page, you have a lot of case studies. For example, they have case studies on Netflix, Zillow, and so on. Some companies which use Kafka for various things. For example, Zillow does it for the moment you get a new house onto the market, it gets that information, immediately sends to an ML model, which generates a Zestimate or some sort of an estimate for how much the price of the house should be, and sends it back to a front-end server from which other people have access. Zillow can immediately see the estimated price, for example. Right? And there's also Google PubSub, which is a managed service, which is very similar. It's also a streaming platform. There's also Apache Flume, which is an open source streaming platform. So they all have differences and slight differences in strengths and benefits. It's good to go through their quick start documents. Finally, the Spark streaming recommendation example that we did was using Scikit Surprise. maybe change it to PyTorch or MLlib if possible, and see, experiment with that. And anyway, Databricks computation is free, so you should try it out. So let me now switch gears and talk about online experimentation. So um, so here our focus is not on deployment, but to evaluate our deployed model. Okay, we can always train our model and get evaluation numbers from validation data sets. For example, let's say it's supervised learning on offline data, as in previously collected data. But to convince your business stakeholders that your new solution is actually effective, you typically need to do a randomized control trial, and that's what an A/B testing is. So some of you who attended my other lecture from my other class, you already have heard about this, but let me still go through basics of A/B testing, and hopefully we'll get to see an example of a minimum, I guess, code base which does the A/B testing experiment. Okay, we'll use Flask and a supporting package to do that. Okay. But first, let's look at the A/B testing basics. So A/B tests are essentially split tests, or are also called randomized control trials. And they are a data-driven way to prove to business stakeholders that your new solution, let's say a new prediction model, gives a tangible lift. People call it uplift or lift to appropriate business metric like sales or conversion or engagement or whatever. Okay? And it could be anything else, but I'm talking in the context of internet, products and services. The advantage and disadvantage of A/B testing is that A/B testing is easy to understand and easy to deploy. But at the same time, it's easy to misinterpret the outcomes and misuse A/B testing itself. Okay. Using A/B testing while doing ML model deployments is a great way to hedge risks, right? So, for example, you could have your new improved version of your model. You could roll out on a smaller set of users, and then also do A/B testing to figure out whether it actually gives it performs better or not, and then roll out to rest of the users, for example. There are other tools, I would say sometimes even sometimes better, which are called multi-on bandits and variants, which address this issue of A/B testing being reliant on hypothesis tests, as well as being sometimes inefficient. For example, you may be subjecting users to an inefficient or not inefficient, but a poorly performing machine learning model for a long period of time. You can, and so some chunk of your users are experiencing, I guess, a bad performance. You can minimize that using other techniques. So one of them is called multi-on bandits. Okay. Anyway, but let's focus on A/B testing for this session. So there are many vendors, many professional vendors, and you will see lots and lots of implementations on GitHub. Like for example, Expand, Wasabi, and so on. And Flask itself has a small A/B testing add-on or extension called Flask Split. So we'll look at we'll actually look at one of these guys, one of the non-commercial or one open source implementation called Planout by some researchers at Facebook. We'll just use that as it's a very simple and easy to understand I guess package, so that we can understand how to set up a A/B test. Okay, and the pattern will be similar the moment you have other vendors or other solutions. So before we get into the details of A/B tests, so I want to tell two things. One is the setup itself. So A/B test, in terms, you can think of it in terms of two things. One is actually running what is called an experiment. So inside an experiment, you have, let's say, a baseline model, which is the existing ML model, and let's say a new ML model that you generated. Let's say both are movie recommendation models. So you an A/B test basically, has two phases. One is to collect the data. So while collecting the data, what you're going to do is for every new user who logs in. So let's say you want to start the experiment. So you have both the models ready to make recommendations. So every time for the next 1 month, every time a user comes in, what you can do is randomly make them experience the recommendations from one ML model or the other ML model. So since they're only in my example, since there are only two models, M model 1, model 2, you can just flip a coin, a fair coin, and if it lands heads, make them experience the baseline ML model, and if it lands tails, make them experience the new ML model that you've developed. Okay. So you do this for a month, or generally, for now, some number of user logins or some number of users, what would be the choice, and you do that. And at the end of that, you collect data for each subset of users who have been exposed to model 1 and model 2. Okay, so for both models, we'll have a bunch of data that we collect, right? Like how much did the users engage with the recommended movies? Did they actually click on the recommended movies? Did they complete the movies? Or things like that. Okay, so that's the data collection part. And the second part is actually use the data for an appropriate hypothesis test, which will tell you whether model 1 is better than model 2, or basically baseline is better than your improved model, or whether your improved model actually gives you the lift that you thought you could get from the new model. Okay, so that's the two parts. We'll not spend much time on so the next comment, so the next section, what we're going to talk about is about this some nuance about this data collection, and after that we're going to talk about the tests themselves, and then we're going to do a practice with this Planout open source package. Okay, so data collection seems quite straightforward, but there is a nuance that I want to call out, which is this notion of bandit feedback. Okay, so bandit feedback, it just means that uh, so this is a term basically which is borrowed from the machine learning research community, which itself borrows it from the casino or gambling vocabulary. The idea is basically very straightforward. The idea is that we only receive feedback, say from the user, on the decision that we took. Like we recommended, 10 movies. We only get feedback on those, how did those 10 movies fare, or that recommendations fare, and we don't have any idea of what would have happened if we showed a different set of recommendations. Okay, so so this is what is called bandit feedback. You only get a response or a feedback on what you showed, and not the 100 other things you could have shown but you did not show. Okay, so this is different from what you would see in for example, supervised learning, where if you predict, let's say, an image is a cat, maybe you can get feedback which will say that the image is actually a dog. Then you also know that if you had said dog, it would have been correct. If you had said fox, it would have been wrong. Okay, so you also know what would have happened if you had done something else. Okay, that setting is called full information setting. Okay, full information feedback setting, where one would not only know how to score your own decision. Let's say you predicted cat, which turned out to be wrong, but you also know how to score anything else that you could have predicted. Okay. And so that there are a couple of examples here, but let me just focus on example 2, which is relevant to our recommendation setup, is that that the feedback obtained from a recommendation system can be considered both, depending on appropriate assumptions or rationale, can be considered as both full information feedback as well as bandit feedback. Okay, so for example, let's say we deployed a model and it's, as usual, is generating a list of recommended movies. And let's say this list, sometimes after post processing, because sometimes you don't want to, you only want to show 2 or 3 movies of each genre or something like that. Okay, after that, some post processing, it was shown to the user. The user may give some feedback, right? For example, they may interact with the recommended movies, and they may click, they may view some of the movies, and so on. And we collected information to hopefully eventually figure out how our recommendation list was. So to do that, so we collected this information of feedback of what the user did. Now, let's say we are able to assess how good this particular list was. And so to do that, we can think of having something called a score, we can think of having a score function, right? A score function has 2 inputs. One is the recommended list, and what did the user actually do? Okay, so given these two, we can say, oh, whether the list was good or not. if we have this explicit score function, then we can also score how the, we can change the first input to the list that, instead of the list that we actually showed, other lists. Okay, if we have the score function, if we change the input to other lists, we have the user feedback already. We can score other lists, and therefore this will be considered a full information feedback. But if we did not have, such a rich scoring function, such a good scoring function, then we only know how the current recommendation list fared. We don't know how, if you change the list to something else, how would the user, how would the user's interaction pattern would have changed. Okay, so each perspective, assuming something is full information feedback or partial or banded feedback, just depends on what you think. Do you have a good handle on the score function or not? Okay, so this is just a nuance on the data collection aspect. Now let's move on to the tests themselves. So as I said, the first part of A/B testing, which is to just collect the data, involves essentially randomizing. So if, let's assume for the rest of the narrative that we are only having two models, a baseline model and a new model, that ML model that we come up with. So so in the first phase, when we are doing the A/B test setup itself, we just have to, if we have 100 users, we just have to somehow arbitrarily put, not arbitrary, sorry, randomly put with equal probability, put a user into, expose them to the baseline model's predictions or baseline model's recommendations, and with equal probability expose users to the new model's recommendations. Okay, so that part is clear. Now, once we collect the data of, let's say, click events or screen time events or something like that, then we can do a test. Okay, based on these measurements, whether one measurement is certainly, is statistically significantly better than the other. Okay, so for that, we can, I'm going to describe very quickly two or three different tests, actually three different tests to that we can answer. Okay, so that we can use to answer, to make a decision whether the machine learning model is better, the new model is better, or is the baseline model still, it's it's unclear if the new model that you've developed is better or not. Okay, so the three tests that we will quickly discuss is a two sample t-test. And so all of these are related to samples, because we have data from the A version, the baseline machine learning model, and we also have data from the B version, which is the new machine learning model, right? So the three tests are two sample t-tests, a chi-square test, and Poisson means test. Okay, and they answer slightly different KPIs or business metrics that you are interested in. So depending on, you made all sorts of measurements of user engagement after they were binned into being exposed to the first recommendation engine or the second recommendation model. But depending on your question, you may want to use different tests, and there's always going to be many tests, which could be which could change based on the question. But for the same question, also there could be many tests. Okay, for example, instead of the Poisson means test, you can use a non-parametric test called Mann-Whitney U test. Okay, so but let's talk about. So we're gonna spend a little bit time on like which questions are being answered by these three, because these three are the typical tests that you will see. If you deploy a machine learning model, or many or other questions which you see with internet companies. But before that, I want to talk about uh, uh, some basic considerations in any test. Okay, so it's not specific to like one of these tests is specific. It's general for all tests. Okay, and what is this consideration? It's about the sample size. How many users are you like? How long are you supposed to run the experiment? Right. So for that, we'll have two terms, technical terms. Um, okay. One term is just sample size, which is just the number of users, or the number of number of users that need to be exposed to the treatment. Treatment and control are A and are B and A, basically, to conclusively reject or not reject the null hypothesis. So sample size is the number of users. So if you have 2,000 users, maybe about 1,000 users for control, 1,000 users for variation, or basically 1,000 users for baseline model, 1,000 users for your new model. Okay, but why the 1,000, right? So that depends on another thing called the another quantity called the minimum detectable effect. Okay, so minimum detectable effect just means, let's say the baseline model, machine learning model, which is making recommendations, has a certain performance metric. Okay, so let's say it's clicks. Okay, how many out of the recommended 10 movies that I'm showing, how many movies on average is the user clicking on? Okay, let's say that's a simple metric. So maybe they're clicking on 30% of the movies being recommended. Okay, so 30% is the baseline metric. Okay, the minimum detectable effect is the is your uh, preconceived estimate, or a priori estimate before you run the experiment, is an estimate of what you think is the improvement over this baseline metric. Okay, if it's 30%, baseline model is making people click 30% of the time, uh, and if your model, if you're estimating that it'll allow you to it'll increase the clicks to 35%, then 5% is your effect size that you're hoping that you'll get, and you want to pick a test which will at least detect that much of effect size, which is 5%, let's say absolute, or it could be relative, but let's say absolute. So minimum detectable effect is a minimum effect or improvement that a test can detect. Okay, and the longer the test runs, which is more and more users you're running the test for, the smaller the effect that the minimum detectable effect that you can detect can be small. Okay, but if you're running a test for a very short period or a very small number of users, the minimum detectable effect that you can detect, cannot be small. So if you can only detect things which are highly influential, like have a huge lift, for example. Okay. There are, so for a general test, as I said, there are few things. One is sample size, how long to run the test. That will influence the hypothesis test performance, as in how many users are exposed per variation, essentially. But also some other things are properties of a test. One is called the statistical power of the test, which is which is of course influenced by how many users you expose to in each of your control and treatment. And a power is nothing but the probability with which, if there is actually a minimum detectable effect, which is that your new model was actually better than the baseline model by some percentage, let's say absolute, that you will be able to detect it. In the sense, so power of a test is basically, if your new model is better, can you say that your new model is better? Okay, so the probability with which you can do that is essentially the power of the test. And there's another quantity called significance level, which is the probability with which the test will say that will make a mistake and say that we found an effect, as if the new model is actually better, when in reality it is not better. Okay, so it's significance level is some sort of a sense of the test can make a mistake. Okay, so when the ground truth is that the new model is not better, there's a small chance that the hypothesis test can say it is better. Okay, so what is the small chance? That's alpha. Okay, and this is something that you choose. So out of the parameters like alpha, beta, which is related to the power, and sample size, and minimum detectable effect, you get to choose, let's say, three of them. So you get to choose, let's say, alpha, you want a certain significance level, and let's say you want to detect a minimum detectable size of some percentage, then, and let's say you choose the power to be 1 minus, let's say beta is 20%, so 80% power, then your sample size is automatically determined. Okay. Um, so here's an example from Optimizely. I'm not sure if it's going to work. Yeah. So you can see here. So if your baseline conversion rate, conversion just means that whatever event you care about after you treatment effect measurements. So let's say it's 3, and minimum detectable effect relative, in this case it's relative percentage, is 20%, and we are saying alpha is 5%. Okay, then the sample size you need is 13,000. Okay, now, if I say minimum detectable effect is 2%, you can see the sample size that we need to be able to detect this such a small effect is 2 million. Okay, so that is what I wanted to mention there. So now let's come back and talk about these 3 tests that I briefly mentioned earlier, mostly about what is the question that they can answer. Okay, the 2 sample t-test and related variants, which are just changed based on the assumptions you make, can help you answer the following question: is there a difference in the average value of the metric that you're computing across 2 groups? Okay, so for the baseline model, for the new machine learning model, you can get the average metric that you care about, like average click rate or average time spent under each of the recommendation engines. And then you're saying whether these 2 average numbers are they, you have these 2 average numbers, but you're asking under these 2 models, the population mean metrics are the same or not. Okay, you have, of course, data. You can answer this question of whether the population means are the same by using the data you collected from the randomized control trial. Okay, so as in from the data that you collected from the randomized control trial, you can compute the sample means, and you can from that you can compute what is called a t-statistic, for example, and use a t-statistic to be able to compute what is called a p-value. Okay, which is the probability of observing the data that you saw, or the probability of observing the t-statistic that we see, given that the under the assumption that the 2 population means should actually be equal. Okay, so under that assumption, what is the probability of me observing the data that I've observed? If that probability is really, really small, then you can reject the null, saying that the means are the same. Okay, and you can actually see that here. Okay, uh, so here's an example tool demo. So here's the sample, first variation. Here's the second variation, and here, we are trying to figure out whether sample 1 is, so the hypothesis is that both the D here is the difference. The difference is the same. Okay, that's the under that hypothesis. What we observed is that sample 1 is having a mean of 58 units, and sample 2 has a mean of 33 units. The question is whether we can reject this null or not. Okay, so we can do that. So we can, given this data, we can actually say that sample 1 mean is greater than sample 2. But what if we increase our confidence? So the moment I move from 97% confidence, which just means that I want to make the p-value should be lesser than p-value should be less than 0.03, then the test is not able to reject the null that the difference is, there's no difference. Okay, so you can actually play around with these numbers. So you can see that if I reduce the confidence, if I'm willing to accept a p-value greater than, p-value less than 0.2, then we can actually get the verdict that sample 1 mean is greater. Okay, so yeah, so you can play around with this. You can change these numbers, but we will see another example when we actually deploy our model. So it will become more clearer then. Okay. We'll actually do 2 sample t-tests for our recommendation models in the next few minutes. So now let's focus on the next couple of tests. We'll not go into the detail, but they answer a slightly different question. So chi-squared test answers the following question: is there a difference in the rates of success across 2 groups? Now, what do I mean? What do we mean by rates of success? So here you can actually think of actually like people going all the way to a checkout page, or uh, people actually completing a movie out of the recommendation list. So out of the 100 times you gave recommendations, maybe only 14 times they completed a movie from the recommendation list. Okay, under one model. And in the second model, they completed the movie 20 completed a movie, at least one movie from the recommended list only 20 times out of the 100 times you made the recommendation. So this is a rate. This is a number between 0 and 1, right? So you can check whether whether these 2 numbers are different based on a chi-square test. And again, it's the same idea. If you reduce the confidence level low, it's not changing. But if you change the sample, let's say it's clearly different, then you can see that you get the verdict. And even if I bring it back to 95%, you can see that we can still say that sample 2 is better. But if I increase the confidence level quite a lot more, okay, it didn't change. But what if I come back to 40? No, 30. Oh, wow. 25. So now you can see that this, because I'm being very stringent with my rejection of the null hypothesis, I am not able to reject the null given these observations. But if I start moving down, you can see that at 95% confidence, we can actually say that sample 2 is more successful. Okay. But okay, so although I'm changing these parameters here, before you do the test, you have to choose beforehand what is the alpha, what is the sample size, and what is the power, and so on. Okay, so the test parameters are already set beforehand. Yes, that's chi-square test, and similarly, Poisson means test is for looking at counts. Okay, so looking at is the rate of arrival of events, or a rate of it's basically dealing with count of events, different across 2 time periods or across 2 groups. So by which I mean, for example, count of successful content interactions. It's just counting number, right? So you're just saying, oh, once this user is exposed to this recommendation engine, the number of clicks that are happening over the next 10 days or next 10 hours, what is the number of clicks, and is the number of clicks different across the 2 populations. Okay, so you can click on this again, this demo. You can see this is essentially like a Poisson rate of arrival. Okay, rate of arrival of events. So if 20 events per day versus 25 events per day or per time period, then you can ask whether they're different or not. And so we are just comparing 2 Poissons. The null hypothesis is that there are 2 groups, 2 Poisson distributions, but with the same mean arrival rate. And then what we observe is these 2 numbers. Now we're asking, what is the probability that we observe this given the null that the 2 Poisson distributions are not different. Okay, and if you observe these 2 numbers, then there is no difference at 95% confidence. But if I decrease it to 80%, even then there's no difference. Let's say make it 0, then you can clearly see that saying p-value is less than 0.001. Okay, yeah. So those are the tests. Now, how to remember so many tests is one thing is you have to you can remember a small set of tests, right? About 4 or 5, depending on what are the popular questions that you can ask from your business point of view. Another way is to map all these hypothesis tests to linear models coefficient testing. So some of you folks who did, for example, linear regression, in linear regression, under assumptions about the data, you can test whether the coefficient is 0 or not, right? So actually you can map many of the hypothesis tests to that type of setting so that you have a sense of because linear models are something that we worked quite a bit on to get significant coefficients and so on. So many of the hypotheses can be mapped back to an appropriate linear model. Okay, and here are there are links provided here which discuss the same. Okay. Now, finally, before we do the practice of setting up a test for our recommendation model, let's quickly discuss a couple of gotchas or a couple of issues that you should be careful about. The first is misunderstanding of what p-value means. Okay, so if you know it's good that both the business stakeholders and everybody is clear on what p-value means. This is the probability of observing something under the distribution governed by the null hypothesis. Okay, and if the p-value is small, then what I observed is unlikely, and therefore I can reject the null. Okay, that's the idea. Most classical tests are, at least the ones we discussed here, are what I call fixed horizon tests. Okay, in the sense that I pre-decide the number of samples, number of users that I need to expose for each variation. Okay, whereas there is actually there are some testing techniques where you can actually change the number of users that you expose for each variation. Okay, for example, in bandits, you change this dynamically, but it's not a hypothesis test there. So um, um, so this fixed horizon. So what does it mean at the end of the day? If you are monitoring some let's say you're monitoring the metric every day, although the test is, you're running the experiment, you're monitoring the metric like click rates or something every day, and you can also compute a p-value after every after aggregating some number of observations, right? Because once you have some empirical, because you can always have a running estimate of the test statistic, and based on that you can always compute a p-value. That p-value itself is not indicative whether the success is whether that p-value itself may make you make a decision like stopping the test or something like that, but that is not the right thing to do. So like for example, stopping only um, when that intermediate running p-value that you see is lower than 0.001 is a bad thing to do, and that's called peaking. Okay, uh, peaking as in looking at the results before the test has been terminated. Similarly, there are other things, other aspects to testing, which I think I'll talk about in the next section. But there are there are fixes like sequential experimental designs and Bayesian designs that fix some of these issues, and also bandits and other techniques. So let's now get to a practical aspect. So as I said in the beginning, in the first section, that there are many vendors, commercial vendors, as well as open source implementations. So what we'll do is really develop a very bare bones setup and test two recommendation models. One is going to be from SurpriseLib. We have been using that, and one is going to be from PyTorch. Okay, so the difference between those two models, if you've seen from before, is that we've been using matrix factorization models for both. But in the PyTorch version, there is a additional user bias and item bias that we can incorporate. I mean, that we have incorporated in at least in our versions of the model. Okay. So Planout is this library um, for online field experiments. It was created in, I think, 2014 by some researchers at Facebook. But it's a simple enough framework to use, and you'll see that many of the patterns are similar once you use some other online testing framework. Okay, so to get Planout on, let's install Planout locally. So let's go back to, so let me close all this. Yeah. Okay, so let me do a pip install. Okay, actually, I don't even know which. Okay, so we are in the Conda environment. So let's install Planout. Okay, so next what we'll do is okay. So before we jump into the code, how is a package going to help us? Is in the following. So uh, uh, let me go back to the notes here. So, so this is the key idea here, is that, while deciding to serve the recommendations to the user, let's say when they log in or when they open the page, and in this demo, it's just opening the page. Okay. While deciding to serve the recommendations, Planout Planout helps me decide which recommendation to show to this user, and we can do that consistently. Okay, so basically, a Planout-based experiment object will be created such that it will deterministically assign a user to control or a variation. Okay, and we can remember that, and Planout also has some logging capability, and so we can log what happened after showing those recommendations. Okay, so Yeah, so and Planout basically does the assignment of users to random cohort and lets us read those. So if in subsequent code, when we want to know, oh, which user is this, we can figure out by calling an appropriate function, from an object based on Planout to figure out which cohort the user belongs to. Okay, so let's actually look at the code and then understand it better. So here, so let's say, okay, so how do we figure out which which whether the user is in set A or set B, or basically user is in control or treatment or variation? The way we can do it is for every time, let's say user logs in into your system, you can create an intermediate object. Okay, because the user logs into the system, you know what the user ID is roughly, right? Or some unique feature of that logged in user. You can use that and create an object, intermediate object, and that object you can do a dot get and tell and inform yourself of which cohort the user belongs to. Okay, and so that is the that's as simple as figuring out which recommendation you want to serve. So the user is passed to essentially some Planout based class that I create, will create, and that will create an object for us. And using that object, we'll figure out whether this user is in set A or set B. Okay, that's what it is. And what is this class? The class is pretty simple. It's a it's we're calling it model experiment. It's an experiment class. All it says is I think it's better to see this in a notebook. Let's see. Sure. It. Yeah, so let's see here. So what is this class? The class is nothing but, so don't worry about the setup. Setup is just saying where to log some information. But this class is basically saying, oh, given the user ID, I'm going to flip a coin. That's through an internal function called Bernoulli trap with equal bias. I'll pass the user ID, and based on that, I will figure out whether this user should be, use PyTorch as a saying, use a PyTorch recommendation model, or use the surprise lib model. So I'm just saying if params dot use PyTorch is set to 1 or 0. If it's 1, then this person should be exposed to the PyTorch model. If it's 0, this person should be exposed to the surprise model. And when I'm getting 1 or 0, I'm just flipping a coin here, basically. Okay, so this is the class. When we instantiate an object of this class by passing the user ID, then essentially this assign function is called internally, and the user is binned into either the PyTorch variation or the surprise lib based model variation. Okay? And then you can read which control or treatment the user belongs to by just calling the object that we created from this class dot get. Okay, dot get, and we're going to use dot get model type. Model type is the parameter which we are varying. Okay, so let's actually yeah, so we'll run the whole script pretty soon. Oh, actually, we only have less time. So okay, I'm only gonna isolate the key additions here, which is from Planout, get the experiment, define the experiment. The experiment is about model 1 versus model 2, happens to be PyTorch and surprise. Okay, and that's it. And so the rest of the code from line 32 onwards is something that we had in the session 1. Okay, so this is the PyTorch based model, getting top recommendations from PyTorch and getting top recommendations from surprise are just helper functions to get, oh, if it's this model, what is the top 10 recommendations? So if this is surprise type PyTorch model, what's the top 10 recommendations? Okay, and then, okay, so those are helper functions and the model itself. The next part is just reading our models. Okay, so our model is either a PyTorch model or a surprise lib model, right? So I'm just reading both the models. Both are serialized to disk, so I can read it from disk. Okay, using dot load state dict, which is from Torch library, or just use a surprise model load function. Okay, so next is the Flask app that we have created. And so this is the main thing where the predictions are getting generated. So if we created an app, a Flask app, And then let's look at the main function. So this is where the user would come, let's say, onto our recommendation engine. So then we'll see, oh, is the user ID in session? If the user is not in session, I'm just randomly picking a user. So this is just a placeholder code. Ideally, if the user logs in, you would have the user ID somewhere. So given the user ID, what you can do is, as I said, you can create a new object from our model experiment class. And that when you create this object, the user is automatically put into one of the cohorts. Okay, and that information you can get by asking, oh, which cohort is this user from? Is this person in the PyTorch cohort or the surprise lib cohort? Okay, and then if the person is in PyTorch cohort, you can say if model type is PyTorch, then you get recommendations this way. If the user type is surprise, you get the recommendations this way. Okay, and then respond. I just created a HTML to show what the response is. So let's not pass the HTML to show the recommendations. That's not difficult. Next, there are some helper functions to reset and for the user to give us feedback. Okay, so this feedback is where I'm going to run a test on. Okay, so what is the feedback? So let's actually run the Flask notebook to get a sense of it. So okay, I don't have PyTorch installed, so let's see. Okay, so so this is just an interface for me to collect data. So that was not the key. So that is just, so what it does is does the experiment, right? So it creates for each user, puts the user into the PyTorch version or the surprise lib version. But at the end of the day, let's go back here. Once you run that experiment, let's say for a few days or till some number of users are finished, what you'll see is a file like this. Okay, this is a log file. All it's saying is, for example, what is this experiment, at what time, what happened, and you'll see that whether use PyTorch was 0 or 1. If it's 0, it was a surprise event. Sorry, it was the surprise library, and which user it is, and what was the rating of our recommendation. It could be rating, it could be clicks. Okay, it's some fictitious number here. So once you have this log data, once you have this log data, you can do a two sample test. And I just wanted to show you the two sample test. You can just read that log file. So let me run that. We read the log file. And here's log file. It's the same thing. It's just a name, model name, what time, what is the, here it's the same thing as model experiment. User ID is this. This user was put into PyTorch model, and they didn't change anything. So here there are multiple observations for the same user, and there's another user 637 who's in a different cohort, and they didn't rate or anything like that. But I have in the Flask app that I have, users can rate, and so that information is as follows. So users can, depending on which cohort they have, they can rate the recommendations. And in this case, for example, this user is in surprise cohort, or the default baseline model cohort, and here's the rating, and here's the user in the PyTorch cohort, and here's the rating. Okay, so you can subset from that log file basically which variant is the person, is every user in each row, and what is the rating. Okay, let's say we got the rating or the clicks or something like that. Then essentially we have those two data. So data for if they're in the PyTorch cohort, and data if they're in the surprise lib cohort. then a very simple way to do the two sample t-test is to just call from scipy stats t-test and pass the two arrays. Okay, if you pass those two arrays, you actually get the t statistic and the p-value. In this case, in this fictitious data with very low number of observations, the p-value is 0.37, so you cannot reject the hypothesis that both models are kind of the same. Okay, so the effect size here is small. But let's say if you generated random data, so here you can see that I'm generating random uniform distribution between 1 to 5 for data 1 and 3 to 10 for data 2. So here it is clear that if I get 50 numbers from D1 and D2, the two uniform distributions will have two different means. And if I run the t-test, oh wow, okay, scipy is not installed, sorry, not run. Okay, so here you can see that the p-value is really small, which means that you can say that this data, they don't have the same means. Okay, you can reject the null. So that's a example of testing. So simple test using t-test and very simply using the Planout library for putting the users into different cohorts. Okay, so I will not run the flask script, but it's you can run it right after this um, session. So that's all I wanted to cover today. I realized this is the last class. So as just one last remark about this whole course, we saw various things from web servers to serverless to containers to container orchestration. Then we saw managed versions of that. Then we saw PyTorch, sorry, what is it called? Spark batch workflows, and then we saw streaming workflows and the related open source software like Kafka and so on. And finally, we saw experimentation. There were several tools that we could not cover, like Git, continuous integration, and continuous deployment, and so on. But hopefully, those are things that you guys can learn offline or in the next version of this course. So thank you for attending.